this is Junjiro Horikawa, and this is the 25th episode for VEX for Algorithmic Design, and the topic for today is about the extended forces. And it's been a while from the last episode of this series, and the last episode was about the basics of forces. Now previously I was showing the basics of forces, but today I would like to show a bit more advanced stuff for forces, some variety of forces you can implement through VEX. And this is the outline for today's topic. What I'm going to talk to you about is mainly four type of forces. One is attractive force, angular force, motion, and pendulum simulation. And last of all, I'm going to show you how you can implement a spring force using VEX. Now the first force, what I'm going to implement using VEX is called attractive force, which is also called as gravitational force. And this is pretty similar to the force that we have done last episode, which is a gravity force, which is affected by a mass of an object, and in this case the distance between the attracting object and the attracted objects. And the difference between the gravity force and this attractive force is that there is some attracting object, such as this circle, which attract these objects to a certain direction. In this case, all those small objects are trying to go close to this big attracting object. Now each small object has its velocity, which moves the object to a certain direction, and this directional value is going to be updated by adding the force value, which is equal to the acceleration value at each frame. And in this case, the attractor force is the acceleration value. Now let's see how we can calculate this attractor force. Now first of all, let's see what kind of information we need in order to create this gravitational force, attractor force. First, we need to have the mass information for the both attractor and the mover, which is this mass A and mass m. Now we also need to know the direction, in which direction the mover should move to. We can estimate that by calculating the vector values by getting the center points of the attractor and the center point of the mover. Then by subtracting from this point to this point, you will be able to get this arrow value, which is the vector value. In order to define the strength of the attractive force, we also need to know how far is it from the mover to the attractor. The farther it goes, the attracting force will become smaller, so we need to know its length. Let's call this L. And last of all, we need to know the gravitational coefficient for each of the attractor that we're going to use. Well, let's call this G, which also affects the strength of the force. Bigger the G is, then you'll have more forces. And faster the small object or this mover object will come closer to the attractor. Now that we have those information, let's see how we can use these values to estimate the force value. I'm also going to call the directional value as V. I'm also going to assume that this V is the unit vector, which means the length is equal to 1. And let's say that the force that we want to calculate is called F, which is the vector value, which is going to be added to the velocity of this object, of this mover object to move its direction. Now first of all, since this is the vector values, we're going to use this unit V value, which is the directional value going from the mover object to the attractor object. And we are going to multiply this by a strength of the force. Well, I'm going to call this as S. Okay. Now we have to define what S is. And in order to calculate the S, we're going to use the mass for both object and also the distance between the mover object and the attractor object. And also the gravity force, gravity G value, a coefficient value. And the equation looks like this. First of all, we're going to multiply both mass mover, and mass attractor, and also multiply with the g value, which is the coefficient of the gravitational force, and then do the division with n power 2 of L, which is the distance between the mover object and the attractor objects. Okay, so more mass the both object has, you have more speed, you have more strength, higher strength force, and more g, more coefficient g value you have, it's all going to be faster as well. And although the force is going to be decreased by if having a longer distance, meaning happens when you divide it by the power of 2 for the L. And this is the simple form how you can estimate the attractor force going from the mover to the attractor object. And you can say F is equal to B unit value multiplied by mass M multiplied by mass A multiplied by G divided by L square of L. Okay, so this is the equations that we're going to use in order to calculate the attractor force. Simple it is. Let's try to implement it using VEX. Now let's first create a geometry node, and let's go inside. And I'm gonna start by creating two objects, one for the mover object and one for the attractor object. Now I'm gonna start by creating 2 points using different add node, 2 separate add node. And let's create 2 points. And for the add 2, I'm gonna make this add 2 as a attractor points. And for now, I'm gonna set it as 0, 0, 0 for the positions. And for the add 1, I'm gonna use it as a mover object. So I'm going to set it as, let's say, 1 or 10. Okay, so I'm gonna move this point to the x direction by 10. So currently the objects are right here and the attractor is right here. And it's a bit hard to see the points with this single pixel, so I'm gonna use the copy 2 points to apply a sphere onto each of the points. And probably it might be a good idea to set the scale of this point based on the mass of each object. So let's also try to create an attribute to define the mass for both attractor points and the mover points. Okay. Now I'm going to use the attribute create for both of them to define some necessary informations. First, the mass. Okay, and set it as point float. And I'm going to set the mover object, its mass as 1. And for the attractive object, I'm going to set the mass as a bit bigger size, like 5. Now let's also transfer this, copy this move mass attribute for each move component, move object, and the attractor object as a p-scale so that you can also use it with this copy 2 points. So I'm going to create a point wrangle. Copy attribute. And what I'm just going to do is to transfer the mass value to a p-scale. And probably the mass itself might be too big, so I'm going to multiply by 0.2. Same for the attractor object. And now let's try to move the sphere at each of the point using this B scale and a point. Looks like these. Probably I could raise up the multiplication a bit more, like 0.5. Yeah, I think that's good. It's fine. Now let's go with these setup. Now the second attributes that I would like to set is the gravitational coefficient value for the attractor. So for the attractor, going into the attribute create, I'm going to create another attribute for the point, and I'm going to call this gravitation and set as a float. And you can define like any kinds of values for this one. I'm going to say 0.5 as a value. Now since we are creating a force and I want to show you as an animation, we're going to use a solver in order to calculate the force at each frame and move the object using its velocity. So we also need to have this velocity value as well for each object, not for each object, since the attractor in this case doesn't move. So I'm only going to move this mover object. So I'm going to create the velocity attribute just for this mover object. So let's call this vel. And in this case, this has to be a vector value. I'm gonna stop by 0, 0, 0. Now everything is ready in order to start calculating the force. So let's create the solver and try to calculate it inside the solver and try to move the object. So what we want to move is this mover object. So I'm going to connect this point to the first input, and the attractor force point, attractor object point is going to be the second input of the solver for a reference. Okay, now go inside the solver by double clicking it. Now since we are moving the mover object, we're going to create the attractor force using the point wrangle connecting to this previous frame, which is the mover object. And we're also going to refer to the attractor point, which is coming from this input to connect it to the second input of this point wrangle. And let's call this attractor force. Okay, let's open up the code editor. Now, let's try to see what kind of information we need to get. So first of all, we need to have the mass for both objects and also the length between the two objects. So let's try to retrieve that first. So the mass, I'm going to create called mass move for the current mass, which you can directly access to the float a attribute from the current point. Also, let's try to get the mass A, which is the mass for the attractor, which you can use the point function from the second input called mass. And there is only one attractor point, so I can just access to the first point. Okay, let's also get the lengths between the 2 point positions. In order to do that, we need to know the attractor point positions. So let's also do that. Vector attractor pos is equal to 0.1 p at 0. Okay. Now, at this moment, we can calculate the lengths distance between the current point positions, which is at p for the mover object and to the attractor point positions. Alright, now let's also try to get the gravity coefficient value, which is applied as an attribute to the attractor. So let's call this G, getting from the point second input. The name was gravitation and at 0. Okay, let's set this to apply. Make sure that you don't get any errors. Now, next value I would like to get is this velocity value. I mean the the directional value going from the mover object to the attractor object, and make it as a unit vector. So let's also do that. I'm gonna call this as V, which you can calculate it by subtracting the attractor path by a current point positions, which is going to be the directional value going from the mover object to the attractor positions, and normalizing it to make it as a unit vector, which means the length of the vector is equal to 1. Now I think I have all the necessary information in order to calculate the attractive force. Let's try to use all these to calculate the force. Now let's go back to the sketch to see the equations. So it was unit V multiplied by mass of the mover and mass of the attractor, and the gravitation divided by the square of the lengths between the two objects. So let's do that. I am going to call this as a force. And first of all, V, which is the vector unit vector value, multiplied by the mass M and mass A. Okay, then I'm going to multiply it by the gravitational coefficient value, and then last of all, divide with a square of the L, so L times L. Okay, and basically this is going to be the force value in order to move the object from a current point positions to the actual point positions. Now, thing is that there is a bit of problem with this equations. If you look at it, especially if you look at this part, if you divide, it is dividing by the lengths to specify the strength of the attractive force. But the thing is that when this value becomes really close, when two objects becomes really close, well, let's say the distance is like 0.01, then if you multiply 0.01 by 0.01, you get 0.0001. Then if you divide these value by this small number, you get really high value. Makes the force value to be exaggerated, huge, humongous. Okay, so in order to prevent having like really big force like an impact force, we need to kind of limit how much you can apply as a maximum force, okay, as a strength. So let's try to do that. And in order to do that, I'm going to separate this value as an S, just like we did in the sketch. And then I'm going to use a function like minimum to define the maximum force value. So currently S, and let's define the maximum force by, let's say, create the parameter called max force, so that you can control the maximum force to see what's the best balance. Okay, now finally we can multiply this S that has been limited by the max force value to the unit V value. Now all is good. Now that we want to do is to update the point position, but in order to do that we need to first update the velocity value using this force value. So we are going to access to the vel attribute, v at vel, which is the velocity value for the mover object. And what I'm going to do is to add the force vector that I've just created. Then after updating the velocity, I'm going to update the point positions using this velocity. Okay, just like we did for the last episode. This is how you can update the force and use it to move the object. Okay, now let's apply, accept, and see what it does. Now since the updated point object, updated mover object is going to be output from the solver, I'm going to replace the mover point to this point input right here. Now I can merge all those two output, which is the position for the sphere, and let me also color each of these objects so that we can see which one is which. So for the mover object, I'm going to make it as blue or light blue, and for the attractor object, I'm going to set it as red. Okay, now let's see what would happen. I'm going to save this one and I'm going to play it and see. Okay, one thing I forgot to do, let's go back inside the solver, and we need to promote the parameter that I have created, which is this max force. So let's do that first. I'm going to promote this and then set the maximum x force value. Let's start by 1 for now. So the 1 is going to be the maximum of this s value. Okay, let's see. Now going back to this one and play it. Now as you can see, it's a bit too fast and it looks like it's bouncing. So let's try to fix this one. One of the reasons I could think of, which was causing a bit of bouncy movement or too fast movement, is the maximum value for this force value. So let's decrease this value, like let's say 0.2. Let's see what happens with this value. So now if I play it, now the maximum force has been reduced to 0.2 and it's moving way better than before. And you can see that the object is attracted to this big object and moving towards it. And you can actually test this out by changing the attractor point positions manually. Let's say I'm gonna move this right here. And okay, it's not okay. I think I have to reset it. Okay, now it's moving, and if I move this object right here, you can see that the object is being attracted, and farther it goes, it comes really slow, like this. And maybe we might also want to define, like if it's become too far, then the forces become too small. So maybe we might also want to set the maximum force, I mean the minimum force value, so that it doesn't get like close to 0, but strong enough to move the point, even though it's really far. Okay, so let's also do that. I'm going to reset it, and let's also reset the point positions for the attractor. Let's keep this 10, 0. Going back to the solver, and instead of using a minimum, I could use a clamp instead, so that we can set both the minimum and maximum. Now the maximum force is currently this value here, so let's also create a minimum force value, min force. Okay, now let's promote, and let's set this value small but big enough to move the object even if it's really far away. So I'm gonna say like 0.05 or something, see what happens. Okay, Let's see. Okay, where does the main attractor went? Okay, here it is. Oh, it's okay. Where is the main object? Okay, I think the mover object has been moved a little bit, so let's see where that is. Okay, I think I did a little bit of mistake. I also moved this mover object to 10, 0, so I'm gonna set this to 0, 0, 0. Now you can show both object, and let's see what it does if I try to run these simulations. Okay, if I play it. Now, what I would like to try out now is to move this attractor object and see when it gets too far, it still goes closer. Now it's really far away, but it still is being attracted to the object with enough force to move its direction. Now, since the velocity is going to be like incremented by the attractor force, so it's when it gets too far away, it takes a little bit of time to get close to this object. So if it's close enough, then it doesn't have much distance to increment the velocity value, so it's keep the small distance between the object and the attractor. But if you make it really far, then the velocity is going to be incremented really high, which makes the objects go far away like these, which makes it makes the distance between two objects really far. If you want to prevent that, you could also set the maximum velocity value for the object as well. How much, what's the maximum velocity value, what's the maximum speed, how the object will move, which could reduce the speed, the overall speed, so that the distance between two objects is going to be closer and closer. If you want to do that, you can go to the solver and go to the attractor force. And after you have updated the velocity, you could first normalize the current velocity, which makes the length of the velocity is equal to 1, and then multiply by a clamped velocity strength. So first of all, I'm going to refer to the length of the velocity, which is the magnitude of the velocity, and also you can define the maximum speed and get the minimum out of those two values, which means this second parameter that you're going to set is going to be the limitation, like the maximum speed of this object to move. So let's try to show this up as a parameter, and let's call this like 0.5, which might be really fast. Let's say 0.4. See what happens. Now currently it is already really far away. Now if I play it, you can see that the object's speed has been reduced, the maximum to 0.4, so it's going way slower than before. And because of this, it comes really close to this object, and currently it's just got inside the object, which means the speed was not that fast enough. So let's make it 1. Okay, this is still not that fast, but at least it gives you a little bit of bouncing. and the turning speed becomes faster in this case as well. Okay, like you see, it's attracted by its object. All right. Now that's that for the single mover object and the single attractor object. Now what if I want to have multiple objects attracted to a single object, single attractor object? So let's see how we can do that. I am going to first of all create a group and copy this network and try to see how we can create a multiple mover object. And it's pretty simple to do. You just need to make this attractor a multiple points instead of a single point. So let's try to do that. I'm going to first create like a sphere as a polygon, which is currently somewhere around here. Let's make the radius to be 5. Since the mover point is this one. So let's get it here, and I'm going to also create the volume using the ISO offset. Let's make the resolution to 50, and then use the scatter point to create a bunch of points for the mover object. So I'm gonna keep the number to 100. Now I'm going to replace this single mover object with this multiple scattered points. So instead of this single point, I'm just going to replace this, and it works just with this replacement, because what I'm only doing here is setting the mass and velocity for each object and copying the attribute for the mass in order to define the size. And inside here, it's just moving each object based on this mass and gravitational value and the distance. Now, since we have a multiple number of objects, it might be a good idea to change its mass like randomly. So I'm going to the attribute create, then delete the mass value right here, and instead of setting the attributes inside here, I'm going to create the attribute and the mass attribute right here inside a point wrangle before setting the p-scale. So f at mass is equal to a rand based on the current point positions, and let's also set the range, which can be like 0.2 to, what was it before? I don't know, maybe 1.0, and see what happens. Now I'm going to show this up. Now you can see that the object becomes having a variety of sizes, and it will affect the speed how these objects move toward the attractor. Now let's make the positions of the attractor to be a bit closer to the object. Okay, somewhere around here, and let's see what happens. Somewhere close enough. Alright, if I play it, okay, might be too fast, so I'm going to make this slower by in this case setting the gravitation value a bit smaller. So let's go to the attribute create for the attractor, and let's set the initial value for the gravitation to be 0.1 and see what happens. If I play it, now the speed become a little bit slower, I think. Now it's might be a bit fast still. Let's try to move this, see what happens. It might not be that obvious, but the thing is that smaller the mass is, the slower the object should move. Doesn't really see much changes because I guess that there's not much difference in the mass right here. So let's try to make it exaggerated, like from 0.1 to like 5. Let's reset it. Now currently the scale is a bit too high, so I'm going to multiply by 0.1. Okay. Let's escape this 10. And let's set this to 0.05. Okay, now let's see what happens with these. If I simulate this, you can see that the small objects becomes a bit slower. And the bigger objects is moving faster. Okay, let me try this again. If I try to move this object far away. Okay, thing is that I set the limitation for the speed for each object, so it's moving at the constant speed when it reaches above 0.2, was it, inside here. So I guess I need to make this a bit more stronger in order to test out the speed difference. Okay, you can now see that the small objects are moving, but the bigger object is staying at the center of the object, center of this attractor object. Okay. But you could see that the attractor force is working for every mover object. And based on the distance and the mass, it's changing its behaviors. Okay, that's what I wanted to show. Okay, now looks more interesting. All right, so that's good. The next thing I would like to show you is then how you could create a multiple number of attractors. Currently, I'm just using a single attractor to move the whole mover objects, but what if we have a multiple number of attractors? So that that's when this gravitational force becomes more interesting than the gravity, because for the gravity you had only one kind of force moving to the uniform direction, but by using this attractor force, you'll be able to set as many number of attractor as possible, and you can also set a different mass for each attractor as well to create a different strengths for the gravitation. Okay, which could be really interesting, so let's also try to do that. What I'm gonna do, I'm going to copy the network that I've just created and try to change some of it to make it multiple attractors. So this is the point where I am creating the attractor point. Currently it's a single point, so I'm going to replace this with a many number of points. So same things I did here, I'm going to copy this right here. And let's try to move the sphere a little bit to the right by setting the center of the attractor to, or maybe set the 0 and set the radius of the sphere to be really big, like 30 or maybe 50. Okay, Now let's create a volume and then scatter the point inside. Now, I don't want like too many attractors, so I'm gonna keep it like 4 or 5. 4 is fine, I think. I'm gonna connect this. Instead of the single point, I'm gonna connect this to the attribute create, which will create a both gravitation and the math. The mass currently is the same, so let's also make it randomish. So I'm going to delete this math attribute right here. For the gravitation, I'm gonna keep it as a single force value to see the difference by changing the mass. Okay, so for the gravitation, I'm gonna make this back to 0.5, and let's go to this point wrangle and set a random mass for each object, for each attractor objects. Okay, now I'm going to set the mass is equal to let's say rand at p end. I would like to make this bigger than the mover object. So let's try to copy all these and make this range a bit bigger. So from, I don't know, 10 to 20, or maybe bigger, 20 to 50. And let's see what that does. Okay, maybe the distance between those points and the attractor is a bit too far, so I'm going to set the radius with the sphere to be 30. Okay, which might be good, maybe 40. Let's also set the mass for the attractor to be a bit bigger, so 30 to 80. Alright, that's good. Now let's see what happens here. In order to use the multiple attractors, I also have to change things a little bit inside the solver as well, because I'm also only referring to the first attractor points currently. So let's go inside and see where I need to change. Okay, so currently, as you can see, you are only looking at the second input, the first point from the second input. So this is where we need to change for this value and this position value. Let's see for the others. Okay, so only those two values. And for each attractors, we want to calculate an individual different attractor force and then add it all together as a total force, and then add it to this velocity at the end. So let's try to do that. So in order to do that, we are going to make a for loop in order to access all the attractor points first. So for int I is equal to 1 until endpoints from the second input, which counts the maximum number from the second input, and we go until somewhere around here, until we create the force value. Now we can also set the values which is not related to the second input outside here, like just like the mass of the current object. But I guess I don't have that kind of values right here. Everything is related to the second input, the attractor point position, so I'm just gonna keep it like these. Okay, now what we need to change is this reference point number for the second input, which is the attractor points. Same for this one. And the gravitation value, this one. And everything else is just fine with this. And the force has been calculated. Now we also need to create a total force in order to append this force value. So vector total force is equal to 0, 0, 0. And then after we have created the force, I'm going to add this total force. This force into a total force. And replace this force with the total force. Alright. Now we might want to set the maximum speed to something bigger, I guess. Let's make this total maximum force to 1 and maximum speed to, let's say, 5 or 2. If I make it too fast, then it will just jump to somewhere else. So you need to kind of seek the balance. What's the best value? Okay, now let's see what it does. You can see that these objects are being affected by 2 of the attractors, which is close enough to attract both. And if I try to move one of the points, which I should be able to control, getting this one, and let's see if I can move it. Okay, let me stop this. Let me try to select this one and try to move this and see what happens. Okay, now if I move it, if I play it, and if I move this attractor a little bit close, now I can see that it's also changed its mass. Now I can see that the point position is affected by the position of this attractor. Now I guess the affection between those two attractors is a bit too large compared to these two. So let's also try to fix that. I'm going to reset this, and then I think it's due to the mass value right here, so I'm going to make the difference a bit too smaller. Let's say from 30 to 40. Alright. Let's see what happens if I play it. Okay, still being affected to the closest attractor forces. Okay, let's try to create more attractor points. Let's say like 9 or 10. Okay. I think it's doing what it should do. If we want these points to be affected by all these on real time, we might also need to move the attractor points as well. Now, in order to see the difference between the movement, I'm changing some parameters inside the solver for the attractor force. I have just set the max force to somewhere around 0.1, the minimum force to 0.01, and maximum speed to 1000, meaning make it unrestricted. Or you can also comment these line out. But no, I am not going to do that. I'm going to keep it as 1000 for now. Now let's see what happens if I play it. Okay, let me reset this. I play it. Now the movement becomes a bit more interesting. I could also try to make this value a bit faster, like 0.5. The whole speed becomes faster. And the mover objects are being affected by the bunch of these attractor points somewhere around here. if I reduce the speed, the maximum speed, and also make the minimum force to be really slow, it's pretty similar to the last result. And what if we could increase this maximum speed? Still pretty much the same. We could also increase this maximum force a little bit. Yeah, it drastically changes the result. And you could also try to change this point positions to see how it affects its movement. Since there are many attractors, it looks like pretty randomish, so I'm going to reduce the number of attractors. If I move it. Okay, this demonstrates a better result for the attractor between the objects and the multiple number of attractors. Now the final step I would like to do for this attractor force is currently I'm using a ball to move the mover object like this, which doesn't really show in which direction these objects are heading to. So I would like to try to create these objects. Looks like it's heading to a specific direction to the attractor, so that we can see in which direction these objects are heading to. You can either use a attractor direction or the velocity direction, and most of the time it's pretty it looks natural by using the velocity heading, velocity direction as a heading direction. So let's try to use that. And it's pretty simple to do. What you just need to do inside a Houdini, you just need to set a normal direction for the heading. Then you can use it together with the copy to points to orient the object toward that direction. So let's do that. First of all, I'm gonna make this movement a bit slower because currently it's a bit too fast. So I'm gonna make it 0.1 for the maximum force. Maybe it's still fast. The reason I want to make it slower because I want to see where it's heading. So 0.01, how does it look like? Now all the objects are being gathered. Like a cloud. Might be interesting, but might be a bit too slow. So 0.05. Okay, good enough. So we can go inside the network, and what I just need to do is go into the attractive force, and then after everything has been done, you can also update the normal direction for the mover object with the current velocity, and let's also make it normalized. Alright, now going back, I'm going to replace the mover object currently I'm using as a sphere, but instead I'm going to use a cube to specify its mover object geometry. So let's try to do that. I'm going to create a cube which should be coming instead of this sphere. So this one was for the mover object, this one's for the Attractor, I think. So let's replace this color node right here. And let's set the square, the box, to show the direction in which direction it's heading. So I'm gonna make it 0.1 for x, 0.1 for z, 0.1 for y, and 0.5 for 0.5 for a z value. Let's see what it looks like. Okay, maybe it's a bit too small. Where is it? It's a bit hard to see. So let's try to increase the scale a little bit. Or I can say 0.25, 0.25, and 2. Okay, that's good. Now I can see kind of a linear shape which represents the velocity direction, which also represents the heading direction, in which direction this geometry is being moving. And you can see that its direction is being affected by these attractors, trying to go to the closest attractor as possible, as much as possible. Let me make this 0.5 by 0.5. And let's make it 5. Big enough to see. Okay, so that's good. As a final touch of this one, let's also try to move these attractor objects randomly inside the space. It's not really necessary, but to make these a bit more interesting. So what I'm gonna do is to create another solver just for these attractor to move randomly inside a space. So the space that I want to work around is inside this bigger sphere. So let's try to do that. I'm going to first of all create a VDV out of this one. With enough low res, doesn't have to be that high res. This is pretty enough. Okay, so it's 20 by 20, maybe a little bit more. Let's also increase the resolutions of this sphere itself to make it a bit more spherish. Right. Now I'm going to create a solver. I'm going to connect these initial point positions for the attractor to this new solver. Okay, and for the VDV, I'm going to make this to the second input. I'm going to use this VDV value, the SDF volume, to determine the gradient so that it won't go outside the space. Now, going inside the solver, I'm going to try to move this object, move the attractor randomly by using a similar method that I did for the mover object, creating a custom force. Okay, now let's name this random walk. So it's not going to be affected by any kind of external object, but it just moves randomly by its own. And to do that, I'm going to use a quill noise to move around the space in 3-dimensionally. First of all, I'm going to create a position vector value in order to use it for the seed for the noise, quill noise at p multiplied by 0.01. Then also I would like to make it as an animation. I'm going to create a vector 4, including the positions for x, y, and z, and then as a last value w, going to use the time-based value in order to create a animated noise field. Now I can create a vector value. Let's call this F1 in terms of force 1, the first force. So curl noise, and using position for vector 4 value. I'm also going to create a F2, which is going to be the second force, which is going to be the boundary force, so that the point will not go outside the overall space sphere, which can be done using this VDV from the second input. So I'm gonna start with the 0, 0, 0 for now. Now let's start to calculate the force 1 value here. I have just created the vector value. What I want to do now is to, based on the, well, actually I think I can just use this force as it is, because I don't really need to spend much time for this calculation thing here. So I'm going to create a final force, which is going to be the addition between the F1 and then F2, and maybe multiply by some K value, the coefficient value. Let's start by 0.1. We don't know what's the good balance between these values. I'm gonna start by 0.1. Now we also need to update this F2 value, which is going to be the boundary based value. So if the point goes outside the base sphere, which is this one, then I want those points to go back inside. So in order to do that, we need to calculate the gradient of the from this VDV, so that we know the direction, in which direction the point should go in order to get back inside this sphere. So to do that, we might also want to check some of the parameters for the VDV from polygon. First of all, fill interior, so that all the inner volume is going to be filled, and also increase a little bit of external by raising up this exterior band voxels, or just use the walled space value like 10, maybe 20. Yeah, I think that's enough. If the points goes too fast, then might lost its way, so maybe 30. Okay, I think that's good enough. Let's go inside. And first thing we want to do is to check whether the current mover point is inside the sphere or not. We can check that by getting the sample from the volume sample from the second input, which is named as surface. And if the value is positive, then that means the point is outside the sphere. We did this in the SDF session of this VEX for Algorithmic Design tutorial series. So if you're curious about this, you can go back to watch how what these exactly means in detail. Okay, so this condition makes it possible to check whether the point is inside or not, and if it's outside, then I'm going to update the F2 value so that the point will go back inside to the sphere. And to do that, I'm going to calculate this volume gradient 1 from the surface at P. Now if it's outside, this volume gradient will give you a vector value going from the center to outward direction. So I'm going to make it as negative, so that the vector value is going to be going in toward the sphere, inside the sphere. Now I think everything is set and I have created the force. Now I can, just like I did for the mover object, I can update the velocity. Then if you can also update the positions, you can by using this velocity value. Alright, looks good. Now let's see what happens. I'm gonna check how these attractor points will move if I play it. And let's also show up the sphere. Now some points went outside at some point, so that's not good. Okay, and that, I think that is because the speed is a bit too fast. Or is it? So, in order to prevent that, we might also need to prevent the maximum speed of this point. So let's try that. I'm going to let me also make sure that if I make this volume gradient to positive, yeah, it still goes out. So that was not the case. We need to limit the speed, the maximum speed. So just like we did for the mover object, we're going to first normalize the velocity, then get the length of the velocity, then use the minimum function to limit the speed. Let's set the maximum velocities as a parameter. Let's make this like 0.5 so that the movement is going to be slow enough to keep inside the sphere. Okay, now the movement of each point becomes slower. We now have those points which stays inside the sphere. That's good. Now let's raise up a little bit of numbers for the points and replace this right here, gravitation. And we can now check how it looks like together with the moving attractor and the attracted mover object. And maybe I could also start this mover object using a little bit more scattered positions like these. It might give you a better result. Okay, now let's see what it does. If I play it. Okay, now problem is by moving its attractor point, the mass is changing dynamically, so that's not really what we want because it's changing its positions. So I'm going, instead of using the position, I'm going to use the PT num instead. So the PT num wouldn't change by the positions. So I'm gonna create some random seed. Alright, now let's play this up. Reset the simulations and try to replay it. Now you can see that Attractor is moving randomly, and also by its positions, the mover object is also affected. Alright, cool. Okay, so that's it for the attractor force that I wanted to show. So let's go to the next topic. The next topic that I would like to talk about is angular force and the motion. For angular force, I would like to show you how you can create a force which you can use to rotate the object around a specific object. For angular motion, I would like to show you how you can rotate its object by its own using a similar method. The idea for the angular force is pretty similar to what we have done for the attractor force. The difference is difference between the attractor force and the angular force is that the attractor force, for the attractor force, we were incrementing the velocity in order to change its direction and the speed. Now instead, the angular force, we're going to increment the angles instead of the velocity vector value. And used by incrementing the angle, the speed of the rotation will increase by time and the amount of rotational as well. So let's see how we can do that. Let's say we have two different objects. One is the mover, and one is the center object, and the mover wants to go around, rotate around this center object. And the information we have right now is same as the attractor force, the distance between the center of each object, let's call this L, and the mass, let's call this mass C, mass, and we have this direction V, and the amount of direction we want to move can be defined by this angle. Checking from the center of the center object, we can define the angle theta to be a amount we want to move at each frame, which is not always the same value as this unit V, so unit B might be a bit smaller, somewhere like this. This is just an angle. So previously we were updating the velocity, which was the vector value, in order to move the object. But in this case, if the rotational axis is in a it's just like one axis, like z-axis or y-axis, then we can just use this single angle value in order to determine in which direction or in the object should move by calculating the rotation rotational matrix and apply to the current point positions. You'll be able to estimate the rotated positions. You'll be able to calculate the rotated positions. And same as the attractive force, we can add the this angle at each frame as a speed to this object to move around this object. So time goes by, and more frames you have, the speed becomes faster, faster, and faster, because every time at each frame you're going to add this angle incrementally, and the speed is going to be really high in the end. So we also need to limit the maximum speed at some point as well, if we want to, if we don't want the really like maximum top speed. Now in Houdini, we're going to try to create an angle using the float, and I'm going to use the matrix in order to create the rotational matrix, and then apply it to the point positions to actually rotate the point as a vector value. So let's try to do that. In terms of the equation, it could be similar to the attractor force, so let's try to create some equations for the attractor for the angular force. Now the final output we want this time is the angle, which is equivalent to a force value, a force vector value in a attractor force. Now we can start the calculation by multiplying to mass again, mass m multiplied by mass c. Since we might be able to assume that this rotational force is being applied or being given by the gravitational force from this center object as an attractor, we could also give a additional like coefficient like g, like gravitation related value. You can skip that as well if you don't need it. Then also based on the distance from the center object and the mover, we can also limit the amount of rotation, how fast the object will rotate based on the distance by setting the same calculations divided by square of L. So the result of the equation is pretty similar to the attractive force. The only difference is that the value that you get as a force is a float value, which is going to be used as an angle. Maybe a bit confusing with A, so I'm gonna call it as F. Okay, now instead of velocity, we're going to add this force value as a float value to the angle, the current angle. So let's say the current angle is equal to A, okay? And by adding F at each frame, you'll be able to increase the speed time by time. And then finally use this A to rotate the object. So maybe the first frame, the A is this much, but in the second frame from here, the speed got faster, and the third frame it's much faster, and so on. Okay, so that's what we want to do. And for the rotation, we can use a matrix rotational matrix calculations for Houdini. So let's see how we can do that. Let's first set up the scene. I'm first going to create a center object by using an add. In this case, I'm just going to create a single point on the center, 0, 0, 0. So this is going to be the center object point position. Now I'm also going to create a bunch of points which is going to rotate around this center object. So to create a bunch of points, I'm going to create a line which is at the x direction. Oops. And let's also set the length to 5. Okay. And I'm also going to scatter some points on top of this curve, on top of this line, so that I have a bunch of points available at random positions. So scatter points. Connect it right here. Let's have around 10 points. Okay. And let's also decrease the relaxed iterations so that we have more randomness. Somewhere around here. Alright. Now first of all, let's try to set some mass for these moving object, rotating object. I'm going to create a point wrangle to set initial attributes. Let's call this init. First thing first, let's try to add a mass. So f at mass is equal to, I'm going to use the random again based on point positions. And also let's remap this in between something really small and something maybe from 0.02 to 0.3. Just gonna make it constant for now. And then based on these mass value, I'm going to also set the p scale. So let's just transfer as it is for now. And then I'm also, I think that's pretty much it for these. Let's also set some attributes for the attractor, I mean the center object. Okay, so for these one, just like the attractor points in the previous sessions or previous topic, I would like to create a gravitation value and the mass. So I'm gonna create, since this is a constant value, I'm gonna create an attribute using attribute create. So first of all, gravitation, and let's say the value is equal to 1. Let's make it 0.5. Okay, now we also need to have a mass. So let's call this mass. And want to make it bigger than these moving points. So let's make it 10. Okay. Now we also want to copy this mass value as a p-scale, so I'm going to do that. I'm going to copy this point wrangle and call it like these. Okay, let's check it out. So I have gravitation, mass, and p-scale for the attractor, and mass and p-scale for the rotating object. Alright. Now, just like we did for the last time, I'm going to use the copy 2 points to visualize these points as a sphere. So, create a sphere. Let's also color this. So this is going to be the rotating or the center object. Let's make this red again. Okay. Which looks pretty big currently. Which might be too big. We might want to reduce this. Now let's also create another sphere. I'm going to color D with the blue for these rotating points. So copy 2 points. Okay, and merge these together. Now obviously the sphere is too big. The center object is too big. So let's reduce the mass a little bit. So currently the mass for this one is pretty small. Let's change the mass for the center object to be something like 3, maybe 2, still big, 1. And let's also move the line a little bit to the right by 1. Okay. I think that's good. Let's try to do with the setup. Okay. Now let's also make the lengths a bit longer so that we can see the difference between each different lengths from the center to each of the point positions, so we can see what what kind of distance will make a difference, and also the mass. All right, looks good. Now I think we are set with the initial setup. Let's create a solver to actually calculate the rotational force, the angular force. So this time we want to rotate these blue one. So I'm gonna rotate these points, connect it to the first input to the solver, and the attractor points will go to the second input as a reference. And as an output, the mover object will be updated. So I'm gonna connect it right here. Now let's go inside and try to implement the force that we're looking for. So I'm gonna do the point wrangle to move all the points, all the mover points, and refer to the center point object to the second input. Let's call this angular force. Now, just like we did for the attractor force, first I'm going to retrieve all the necessary informations. First of all, let's get the center point positions. this vector c pos is equal to point second input p 0, since there's only 1 point. Okay, we could also get the c mass. Well, let's call it mass a, or mass c is 0.1, a mass 0. I'm gonna call this pos c. Okay, and also we can get the gravitation value, so I'm gonna call it g 0.1 gravitation 0, and float distance, which can be calculated by getting the distance between the current point position, the current rotating object positions, and the position c, the center object point position. Alright, I think that's really much it for what we can get as initial value. So we can now use these to calculate the angular force value, which was calculated like these. F is equal to mass m multiplied by mass f, mass c multiplied by gravitation divided by the square of the distance. I guess I should rename some of it based on what I've wrote. Okay, where does this come from? Okay, what's this? I think I'm having a little bit of weird stuff. Okay, so we don't need this. Okay, what's happening here? Okay. So I'm gonna rename this to L, and I'm also going to retrieve the mass M, which is equivalent to getting the mass value from the current point object, the moving object. Alright, so let's calculate the force value as a flow value. First of all, mass m multiplied by mass c multiplied by the gravitational value divided by the square of L. Okay, so pretty similar to the attractor force, isn't it? So that means we also might need to like limit the speed as well, because this could be really fast if the L is really small. Okay, that's what we need to care about. So let's try to do that. I am going to, let's say, f is equal to use the minimum with the f, and let's create the parameter max, like force or max angle. Let's say max force. Okay, need one more parenthesis. All right. Now, after doing this, we could increment the angle attribute, which we haven't created yet. So let's do that first. Let's go back outside for the moving object, which is this point. I'm going to also create an attribute called ang, which is going to be used to rotate the object. It's equivalent to the velocity vector value for attractor force, starting from 0. Okay, now going back. After I've created the F value, the force value, I'm going to increment the angle with this F value. Okay. Now, there is a chance that the F also going to be really fast, so just like we did to limit the speed, we could also limit this angle size as well. So f ang is minimum, f at ang chf max speed, or maybe max angle. Okay, so this has, the max force has to be small enough, like point, I don't know what's the best value for these one. Let's start with the really low value, like 0.1, and this to be 0.3, I don't know, maybe 0.05 for the max force. Okay, now after I have created these angle value, I am going to actually use this to rotate the points around this center object. So to do that, first of all, I'm going to create a rotational matrix by first creating a identity matrix, and then rotate this. Okay, forgot to name the variable. Rotate this identity matrix by the angle that I have as an attribute. Then in this case, I'm going to use the y-axis for the rotation, so 0, 1, 0. Okay, now that I have this rotational matrix that's been created, I'm going to actually rotate these points in each frame. To do that, first thing you need to do is to first reset the center point for the rotation to be right at here, position C. Since this is at 0, 0, 0, you don't really need to do this subtraction, but just in case the center point might change afterwards, I'm going to first of all reset this point position to be 0, 0, 0 by doing this subtraction for the vector. Then apply the rotational matrix, then add back the center point position. Okay, that's just it. Now let's go back and see what it does. I'm going to check the geometry, and if I play it, you can see that the object that is close to the attractor rotates fast, rotates really fast, and then the outside object starts to rotate at the and at some point the speed is going to be maximized, or at the top speed, limited at the top speed. We look back initially, you can see that the object that is close to the attractor is rotating really fast already, and then the objects outside is moving slower, but finally gets to the top speed, and everything is moving at the same speed finally. Now you can also see that the difference between the mass and how much it affects the rotational value. So that if the mass is bigger, then it rotates faster. Just like this. Okay, so pretty similar to the attractive force, but you can you can also use the same idea for something different, like this kind of angular force. And this same idea can be implemented for many other usage. So with your idea, so it could be really interesting if you could find a way, if you could find an additional like custom force for yourself. It's just a matter of how you think, how you like remap this force value to something different. And in the end, you could create a force like a bending or more advanced, more complex force just by increasing these simple method. Right, so that's for the angular force. The next thing I would like to talk about is the angular motion, which is to rotate the object by itself, using its center core as a rotational center, which is pretty similar to the angular force with just what we have just implemented. Only difference is that in Houdini, in order to rotate the object around an center object, we change the position. We rotated the position itself as a vector value. Now instead, for the angular motion, what we could do is to use the change the normal direction, rotate the normal direction of the object in order to do this angular motion. And that is the only difference between the angular force and the angular motion. So let's try to see how we can do that. And since this angular motion is not affected by a attractor force, or I mean the center object, we don't really need to care about the other object's mass or gravitation value, but we can just look at its own mass as a property. So we could assume that this rotational object itself has its coefficient value like g, and it's also have its mass. And just by using these two values, we can estimate its force value. So we could say the force F could be equal to like mass multiplied by g. And that's it. And then we could add this force to an angle. Then we can use this angle to rotate its object. And in this case, what we're going to rotate is the normal direction of the object, which could be this vector value, n. And we're just going to rotate this based on the angle. And the normal direction will change, makes the whole object to rotate at the center, from the center of this object. So it's much easier than the angular force, which was rotating around the object. Okay, so let's try to implement this. First of all, I'm going to copy the previous network, and I'm going to change the shape of this rotation object to be a cube so that it will be easier to see that it's rotating by itself. I'm also going to keep the angular force, but I'm going to also make it a bit more slower because currently it's a bit too fast to see the effect. Okay, so I'm going to a solver and go to the angular force. And let's make the maximum force to be 0.01 and the angular maximum angle to be 0.1, which is equivalent to the speed. Okay, let's see. It's still a bit fast, probably. Let's make it a bit more slower. I'm gonna make it 0.02, 0.005. Okay. Now, it seems like everything is rotating at the same speed, which doesn't really look natural. So I'm going to keep this 0.1. Maybe a little bit more for the maximum goal. Maybe after all, somewhere around here it could be more natural. Okay, it's really up to you. I'm gonna increment this a little bit more. Okay, And you could also change like the gravitational value to be a bit more slower. You could go back to the attractor and right here, gravitation. Currently it's equal to 0.5, so I'm gonna make it 0.1 and see what it does. Okay, this might give you a bit more better result. Okay, and also I'm going to increase the number of object as well. Alright, so with these parameters I'm going to try to create a angular motion for each of the objects. So first I'm going to replace this sphere with the box. So going back to this one was for the attractor, I mean the center object. So I'm going to use the cube for this blue one. And I don't need this network here. Now let's see the size. Size might be a bit too small, so I'm going to make the radius of this box to be 2. Okay, that's good. Now all the other stuff, it's okay. And I would like to have another angular values in order to rotate these objects. So going back to this init 2, I'm going to create another angle related value. I'm gonna just say angle 2 or angle m as a motion. Start from 0.0. Okay. Now going back inside the solver, we're gonna create another point wrangle. In this case, I'm going to calculate the angular motion instead of the angular force. And right here, instead of updating the position like we did right here, I'm going to update the normal direction of this point. Okay, so let's do this. And to do that, we need to have initial normal direction as well. So let's also set that. I'm going to set a normal for each of the rotation object as set 1, 0, 0. Okay. Going back to the solver, I'm gonna name this angular motion. Okay. Now let's first receive all the necessary informations. First of all, we have this mass, which can be accessed from the mass attribute. And we also have the gravitation value float ag, which we might need to set the gravitation value as well inside this init. So let's name this gravitation is equal to any value you want, like 0.1. Okay, and then access to this gravitation value. Now that we have these two values, we could estimate the angle value or the force value. So float force is equal to mass multiplied by g. That's it. Now, now we have this value. I could increment this ang m that we have just created with this force value. And then we could also limit the maximum size for the force and maximum size for the angle as in terms of the speed. So force is equal to minimum force CHF max force, and the angle can be limit using the f at ang m CHF max ang. Okay, so for these values, let's make it a bit larger than the angular force. So 0.2 for the maximum speed and maybe 0.05 for the max force. Okay, now after I have created this angle value, which is going to be incremented at each frame, I'm going to actually use this to rotate the normal direction. The first thing first, I need to create the rotational matrix. I'm going to start by creating an identity matrix like we did last time, and then rotate it using this angle that I have created using y-axis. Then finally rotate the normal direction by the matrix. And let's see. We want to show up this normal direction. If it's really rotating the normal direction, so let's start by showing this one here. I play it. Okay, now I can see that the object itself is also rotating by checking its normal direction. So you can see that it's rotating by itself. Now that we have checked it by going into the visualized object, we could actually see that the object is moving. And in this case, based on the size of the object, the speed should be changing. Although it's a bit hard to see here because it's reaches to the maximum speed really quickly. So instead, I'm going to set the gravity force to be a bit smaller, like 0.01. Now this small object is still slow, but these bigger objects are rotating really fast now. If we go back right here, you can see that this one is rotating slower, but these bigger ones are rotating faster. Now this rotational speed might be able to be affected by the distance between this center object as well if you want. If you want to do that, you could try to do that as well. Maybe that as an exercise. But what I wanted to show you is how you can implement this self-rotation object as a force. And this is how you can do it. Alright, so that's pretty much it. Okay, so that's it for the angular related force. And the next topic that I would like to talk about is the pendulum, creating the pendulum simulations as an advanced example for this rotational force. The next topic that I'm going to talk about as an extended force is pendulum. In order to extend the idea of the angle force, I'm going to show you how you can implement this pendulum as a simulation. A pendulum is a weight, which is its string pinned at the top as a pivot, and then swings based on the gravity, like the sketch shows. And you can simulate this pendulum pretty easily by using the method that I've been showing in order to implement the forces. And in this case, a angular related force. So let's see how we can do that. First of all, let's see what kind of information we can get out of this setup. Okay, first of all, the point right here at the top is going to be fixed, okay, as a pin, so it doesn't move. And we also have this object which has a certain mass for sure. And we also have the length from the center of this object to the pin point, a pivot point. Let's call this L. And when it swings from left to right, how it moves is by making an arc like this. So you can say that it's moving by using an angle. So it's pretty similar to a angular force, how it moves. And only external force that this object has is the gravity force, which is going downward like this. Now the direction this object moves is always have to be on top of this arc, okay? Meaning it's using its gravity to have this directional value which is on top of this arc. In this case, we can get that by projecting this gravity force on top of this arc, and this projected direction is actually the value that we can use to move the object to a certain direction. So by getting the amount of gravity going downward, we can estimate how much it should move to a arc direction, which can be done by using some simple trigonometry. Okay, in this case, if we know how much angle it moves, like let's say we know that amount of theta is moving, which this angle is equal to this value as well. Then we know that this blue angle value or angular force value is equal to a sine of theta multiplied by the gravity length. And we can actually see this as a incrementing angle value, which could be equal to force value, which was coming from the idea from the angular force from the previous section. Okay, meaning F is equal to a gravity, the magnitude of the gravity multiplied by, and we could just say it's G. Let's say this is equal to G. So G multiplied by a sine of theta is the force itself. Okay? Now, and we could also consider the mass of the object as well, which we have right here. So heavier the object is, faster the object moves. So we can also multiply the mass to this calculation or equations. Now we could also use this length as well in order to estimate the speed or the strength of the force. So in this case, the larger the distance, the slower it moves. Could be happen. The shorter the distance, faster it moves. Longer the distance, it moves slower. In this case, we could try dividing this whole equations by L. Now, just like we did for the angular force, we could add the angle with this force. Update the angle with the force by adding to it. Then use this angle to rotate this object. In this case, in terms of Houdini, we could use again the rotational matrix to rotate to move the point position at P attribute based on this angle value. And in theory, by doing it without having any dumping, if the object starts from this angle right here, from the left side, if it goes over to the right side, it should stop at the same angle and then starts to come back to the other direction, and just do the infinite loop from left to right if there is no dumping. Now if you add a dumping, then slowly it tighten the shape, and finally it stops at the center because of the gravity. So the dumping can be considered as something like a friction, air friction. If there is no air, then it infinitely moves from left to right, such as in the space. Or maybe in the space you don't have any gravity, so which wouldn't occur. Okay, so that's it. So let's try to implement this in Houdini, again, using VEX. First thing first, let's try to create an initial setup for the pendulum. First of all, I'm going to create a line. And I'm going to set the direction to -1, so it's going downward. And I'm going to set the length to 5. Okay, and just show this up. Now I'm still seeing those points. I think it's been cached. Let me reopen it. Okay. Now, the point that I would like to move is the second point right here. And I don't really want to move the point which is on the top, so let's try to group the bottom point as a ball to determine which point I should move. So I'm gonna set as a point group. Let's name this ball and 1, which means second point. Okay, now the second point should have been applied as a ball. Let's check that out. Okay, right here. Now, let's also try to get the distance between the top and the bottom. We could just do it using a measure node. Since this is a line, I could calculate its length by setting the parameter, checking the parameter. Alright. Now let's also set some initial attributes to this one. In this case, I would like, I don't want to start the pendulum at this positions, because in this case it doesn't really like move because it's been at the equilibrium already. You need to have this ball to be somewhere around here or somewhere around here so that it will swing back and forth. So let's create the point wrangle. And let's call this init. And I'm gonna create, first of all, some initial angle as a parameter. So f, and I'm gonna say the initial angle to be the radians of ang as a parameter. Let's set this parameter range from 0 to 180. Okay, and I'm gonna stop by, let's say, for 60. So 60 degrees on the left side or right side. Okay, now I also would like to rotate this line based on this initial angle. So to do that, I'm going to calculate the rotational matrix. And in this case, I'm going to use the z-axis as a rotational axis. So let's first create the axis. Axis is equal to set 0, 0, 1. Okay, and also I'm also going to rotate the I would like to also rotate this point position right here. So first of all, I'm going to create a matrix, identity matrix, and then rotate the matrix using the angle that I've created above and with the axis. Okay, now what I want to do is to rotate change these point position. Now the top point position is at the 0, 0, 0, so we don't really need to care about it. We can just rotate the bottom point by multiplying the current point positions by the matrix. Okay, so it's been rotated 60 degrees to the counterclockwise direction, I think. Okay, if I change this, okay, you can check, you can change like initial angle by doing this. Let's set it to 60, maybe 45 might be better. Okay, now after doing this, I am also going to set the velocity. Maybe not the velocity, but in this case, what was I doing? What was I using? Angle, yeah. But the angle is already being used, so I'm just gonna use. I'm just gonna create a new value called velocity as a float, which is going to be the incremented angular value. Although, now that I thought that I already have this angular value, maybe I can just use it as a velocity instead. So I'm just going to delete this and just stay with these to make it more simple. Now the other parameter that I wanted to set, or other attribute that I want to set, is the mass for this bottom object and the gravity force. So gravity value can be applied later inside a solver, so I'm going to say the mass first. Let's start with the 1, or maybe parameterize this one so that we can change this later on. Let's set this to 1 for now. Okay, now I'm also going to create a p-scale, which I'm going to copy this mass value. Maybe 1 is a bit too big, so I'm going to multiply by 0.2 for the as a p-scale. Okay, so that's just it, and I'm also going to create a sphere to copy it into the ball point. Copy 2 point just on the ball group like this. Let's also color this something vivid like red, and let's merge this copied object together with the line, which can be this one. Alright, so this is the initial setup for the pendulum. Then what we want to have is this ball be swinging left to right to left, back and forth. Now I think everything is set as initial attribute and so on, an object. Let's go create a solver again to actually calculate the forces at each frame. So I'm gonna connect this to this first input, and I think that's just it in order to do the calculations. So I'm gonna instead reconnect the network so that the geometry is going to used outside the solver and as an output of the solver. Okay, let's go inside the solver and try to implement this pendulum force. Okay, so I'm going to create a point wrangle, and let's name this pendulum. Now the first thing I would like to do is to get all the necessary informations, so let's do that. First of all, we can get the length of this string from the pivot to the walls, which you can access to the primitive values of the attribute called perimeter. Since there's only one string, I can just say 0. Okay, and I'm calling it L. I'm also going to create a gravity value called G, and I'm gonna create a parameter right here. Maybe I should have created out some. Either way is fine. You can create it either inside a solver or outside a solver. It doesn't really matter where. I'm gonna create the I'm gonna create it inside a solver for this one. Okay, now let's apply. And what else? We also need to get the mass, so which is f at mass. The mass is at the h object. Although there's only one object right here. And probably we also might want to filter this group to ball so that the only ball group will be using this force to move. Okay. Now, I think I have enough informations, and then we could try to calculate the force based on the based on the equations that I've created previously, which looks like this. Force is equal to g multiplied by sine theta, which is equivalent to the current angle, and multiplied by mass divided by L. Okay, so let's see. Going back, and let's try to do the calculations here. So, float force is equal to, first of all, gravity multiplied by mass, and multiplied by the sine of a current angle divided by AL. Now, in this case, there is still a chance that if the L is pretty small, then the force is going to be really high. But in this case, in this kind of setup, the L doesn't really change. So we can control the force value by limiting this G value, like making it really small if this becomes really high. So it's a balance between the L and the G to make the better result, the good result, okay? So for now, I'm not going to limit the maximum speed. If we limit it, then we have a bit of a problem by having this kind of effect that when we try to swing from the left side, if we limit the speed, then the amount of angle we can have at the right side might differ to the left side. Previously, when the half side of the angle is theta, but if we limit the speed, then this, if we go to the right, if the ball goes to the right side, then this angle might be reduced to something smaller. So that's not what we want. So I'm not going to, in this case, in this kind of situations, I'm not going to limit any speed or the force's strengths. Okay. So, and now that I have calculated the force, I can now update the angle. Although, now that I thought that I think I still need the velocity value, because I cannot just update the angle as it is. Angle is just a positional value. But what we need is actually an incremented force value. I mean incremented velocity value, which determines the speed. And angle currently doesn't really shows the speed. It just shows the position, the current point position. So instead of using the angle in order to set it as a speed, I'm going to go back to create an additional velocity attribute. So I'm going to call it as vel and start with the 0. So at the initial position, the speed is equal to 0. Okay, now going back inside the solver, I am going to update the velocity by this force, which is equivalent to acceleration value. Now, I can now then update the angle, the current angle, with this velocity. Okay. Now that I have updated the angle, what I want to do is to re-update the point position based on this value here. So let's do that. Let's do that. In order to do that, what we can do is to first create a directional value going from the top point to the bottom point, then use the rotational matrix to define the point position based on this updated angle value. Now be careful that this angle value is not related to the speed. This velocity value is the speed, which previously previous sections we were calling this velocity as an angle. In this sections we're calling this angle as the positional value. Okay, just like the at p value. Okay, so that's a kind of a difference. Please remember that. Now, so in that case, we're going to first create a vector value going downward to the y direction. Now, I am going to create the rotational matrix using this angle and using z as a axis. Then rotate this direction based on this rotational matrix. And now we can update the point position using this direction, which is currently a unit vector, which means the length is equal to 1. So I'm going to multiply it by the actual length of this string, which is this L. So direction multiply L, and that's the final point positions, the rotated point position. Okay, so I think that's it. If we go back outside the solver and play it. Okay, it's not really moving. I think I'm missing some parameters. If I promote some parameters, okay. I forgot to set this gravity value here. So let's set this to something like 0.5 and see what happens. If I play it, okay, it's rotating the other direction. Now it's totally looking wrong. We gotta fix it. Now let's see what is wrong with this one. I think what's wrong with this one is the direction that we have set for this force right here. Okay, so going back to the sketch, and let me create a sketch again. So we had this gravity force, and we have this angle right here, which is equivalent to, so if we get a sine value in between the sine value of this theta, what we can get is, if this is a unit vector going downward, what we can get is this this value right here. Okay, so that's correct. Now, thing is that depending on the value of this theta, if this is like negative, then the sine value will also be negative, I think. In this case, it's going that way. So that's not good. So in that case, I have to multiply it by a -1 if the theta is negative. So what we can do, we can try to say negative g multiplied by mass to make it as a reverse direction. I think this works. Now let's see what happens. Reset the simulations, and if I play it, now the pendulum seems to work just fine. Okay, and you can see that it's moving from left to right at the same amount, same angle, same speed. And if we try to make it slower, we can make this gravity smaller. Like this. Let's also show the ball. Okay. I'm seeing this cache object again. Okay, looks good. Now let's see what happens if I increase the size of this ball by setting the mass a bit bigger. Let's say 2. Now I think it becomes faster. Let's try with a bit more bigger one, like 5. You can see that it's become much faster. Now let's reset this to 1. Now this time let's try to limit the size of this length. Let's say 2. Now this becomes, I think this becomes faster. If I set this to 1, it becomes much faster. If I set this to 20, it's going to become really slow. Alright, makes sense. Let's reset this to 5. And this time I also would like to set some dumping effect so that at some point the swinging just stops with the gravity and the air friction. Okay, so to do that, you can go inside the solver and try to add the dumping somewhere. In this case, we can multiply this dumping value to this velocity, which is going to be added to the force, added by the force. So FL multiplied by CHF dumping. I'm gonna create some parameter for the dumping and make it really close to 1, but just a little bit smaller, like 9. By doing it, slowly the velocity get close to 0, and at some point the velocity becomes 0, really close to 0, and the object will just stops because of the gravity. Now let's see. You can see that the amount of swinging becomes smaller and smaller by time goes by, and at some point it will try to stop like these. Like this. So what it's doing here is that it's retrieving like 99% of the force of velocity, but because it's decreasing, at some point it just becomes 0. And if I make it like 0.9, then it just quickly stops. Like this is inside the water or something. Right, so that makes sense. Let's make it 995 to make it a bit more natural. Still looks unlimitedly repeating, but it is somehow affected by an air. It's trying to stop at some point. Okay, so that's the simplest form for the pendulum. The next thing I would like to try out is to have a multiple number of pendulum with different size of the lengths and different size of the balls, and array it to see the overall effect. Might be able to create some beautiful graphics out of it. Let's try to do that. It's just a matter of arraying it, but I need to add a little bit of tweaking to the solver inside the solver, because currently I am assuming that the pinpoint is at 0, 0, 0. But if I make multiple number of pendulum, then there's that's not the same case anymore. So let's see. I'm going to first duplicate the network. Let's try to create multiple number of pendulums. Okay, first of all, we need to have a multiple number of lines aligned. Let's align it in, let's say, in Z direction or X direction. In this case, it's rotating. Yeah, I think I can array in Z direction. Let me first reset the simulations. I'm still seeing some caches. Where does it? Okay. Okay, now, first of all, I'm gonna leave this as a basic setup for this group. Can still use it. I'm going to create a for loop for each loop. Let's say use number. Okay, and in here you can determine how many like pendulum you want. Let's say 50. Have enough pendulum to test out. Okay, now let's also create inside a for loop. I'm going to move each line in Z direction. So let's create a point wrangle. Let's name this setup. And then connect this for each count, which has this iteration detail attribute. Can be used to move each point at specific positions. Now, first thing first, I'm going to get the iteration value from the detail from the second input. Also, let's get the number of iterations from the detail. Num iterations. Okay. Now let's try to move this line to the Z direction first. Up p dot z is equal to a iteration. So by moving its point position by a multiplication of 1. Okay, now if I leave the loop, it looks like these. Okay, so next thing I would like to do is to try to change the lengths of the line. Maybe I can start by setting this mass for the same for everything. So I'm going to set the lengths. Let's say first I'm going to determine the minimum lengths as a parameter. Also the maximum lengths for the as a parameter. And then when the point is inside a ball group, which is at the bottom point, I'm going to define its point positions. So let's say float y is equal to fit. I'm going to use the iterations, which is starting from 0 to the number of iteration minus 1, and fit into a minimum and maximum lengths. Okay, now I'm going to update the point positions y value if the point is inside a ball group. So if in point group 0 ball ptnum is equal to 1, then I can set the y value as the value that I've just created. And what I need to do now is to set the lengths for the y, the minimum and the maximum lengths. So let's say the minimum is 2, and the maximum is, let's say, 50. Or okay, and it's going to the opposite direction. I gotta make it negative, so let's make it negative. Okay, just like this. Let's reduce the size a little bit. So it's from 2 to 30, somewhere around here. Looks good. Okay, so let's try with these. And I am also going to set the default angle for this one. Currently, it's at the zero direction, zero angle, which it cannot swing anymore. So I'm just like I did for the previous pendulum, the single pendulum, I need to rotate this. Now there is already a angle right here, a value that I'm setting right here, so I can just use this. And in this case, I think I can just set the mass everything the same because I'm already changing the lengths. It might be a bit confusing to change the mass and the lengths at the same time. So I'm going to set the mass at the same value. So probably I can just leave it right here. Instead, I'm going to place this measure inside the for each loop so that I can calculate it, or maybe I can just do it right here because it's done per primitive, so it's not a big problem. Okay, so I think everything looks great. Let me bring this upward to cover it inside a group. So let me check. So after leaving the group, leaving the for each loop, I have both vol group and not and a primitive. Then I have this parameter, and then set the initial angle and the mass for each group, for each point, which looks good. Now for the angle, we could also limit to the ball just in case. Alright, so everything is good for these initial setup. Now let's go inside a solver, see where I should fix. Because at this moment I think it doesn't really move. It moves really like these. So we gotta fix something inside a solver. Let's see where that is. Okay, first of all, let's rename this to multiple pendulums. Let's see where I should fix. Now, this is obviously the first thing we should fix because it's only looking at the first primitive's parameter. Okay. So, and to do that, probably a good idea is to call the primitive number from the current point number. So let's do that. Int current primitive number is equal to a point prims ptnum. Now this will give you an array, so I'm just gonna get this first one. It's assured that every point is assigned to one of the primitives, so I can just do it like this. Now I can replace this value here with a primitive number. Okay, that's good. Now we also need to know the corresponding pivot position for each ball positions. Previously we were using 0, 0, 0, but now the pivot point position is not at the same position, so we also need to get that value. So to do that, first thing we want to do is to get the point number for that pivot, which corresponds to the current ball point position. So what I can do is to get the array of the PT as, or I can just get our pivot PT is equal to prim points 0 prim, then get the first one, which will be equivalent to the pivot point number. Okay, now that I have this value here, I can now use this one to retrieve the pivot position. So vector pivot pos is equal to point 0 p pivot pt. Okay, now that I have these, let's see where I should use this value right here, this pivot positions. Now, first thing I could think of is this a angle related value. So right here I have retrieved the perimeter. Now getting the gravity, getting the mass, calculating the force, updating the velocity, updating the angle, and updating the angle for the rotation, calculating the rotation. Okay, so I think this is the position, this is a place where I should use this pivot position, because currently at P is just being updated by adding, just by using this rotated direction multiply the length, which in this case it only works when the pivot is equal to 0, 0, 0. So in order to be able to use it for various pivot position, you need to add this pivot position to this. Now all the lines are at the same correct positions. Okay, so I think everything is done. Go back and see what happens if I play it. Now based on the length difference, you see that you are seeing kind of a wavy pattern. It's pretty beautiful, isn't it? And because it has some dumping, it slowly becomes a single line, or try to be straight. Okay, that's good. We could try to increase the initial angle, going somewhere around here. Let's make this really high like these and see what happens. Okay, I think I'm seeing some cache here. Okay, still looks beautiful. That's good. That's good. Let's see if I change the mass of each of the object overall. So let's make it 3 and see what happens. I'm gonna make this back to 60 degrees. So compared to the previous setup, it becomes the movement becomes much faster. Okay, so you could try to, as an exercise, maybe you could try to change the mass for each of the line differently to see what will make it as an effect, which could be really interesting as well. What I could also do as a little bit of tryout is to let's say change this length based on like a trigonometry. Somewhere around here, I could, first of all, I could copy these to make a angular raised value, like 0 to pi multiplied by 2 or 4. And then I could then use the fit 1 1 okay with an iteration, not iteration here, but update the y to minimum length to the maximum length. Maybe I should make a negative right here and positive right here. And I think I'm doing something wrong here. What I need to do, I need to use this y as a sine angle. Okay, how's this? So let's see what it does as the movement. If I play it, not that obvious. Let's make this really long, like 200. That might make it a bit more interesting. And also I'm going to set the mass to be smaller, back to 1. Play it. Yep, looks pretty nice. So this is how you can like create a multiple number of pendulum. It's not really force related, but just to show you how you can extend your forces like these, so that you can try out many forces at once. Alright, that looks good. Okay, so that's it for the pendulum. So let's go to the next topic. And the next topic is now the spring, which is a bit related to the attractor force and the angular force as well, the pendulum force as well. So let's try to do that. Now the last force that I'm going to implement in this session is called spring force. The idea is pretty similar to the attractor force. The difference is that the direction for the velocity is already defined. It cannot freely move, but the two of the object are being connected by a line, and the object can only move on top of this line by some constrained length. If the line becomes too long compared to the constrained length, then it will try to pull to each other. Two objects will try to pull each other. And if the objects are too close to each other compared to the constrained lengths, then the two objects will try to separate using the path of this line to try to get to the constrained lengths as much as possible. And it's one of the basic force you could implement in terms of the particle-based system, which you might have seen it in a lot of places. Like you could also check a vellum or pop grains. There's one called spring force to connect two of the points with the line so that the point wouldn't go farther or to go too close to each other, to keep the certain distance between the points. And it's been often used to create like a object like ropes with a physical property, or you could also use it for clothes as well, like fabric as well, for simulation. Now in today's lesson, I'm just going to show you line-based forces, but by understanding how it works, you could extend it for more complicated, complex situations like clothes, fabric, and so on. So let's first check what kind of information we need in order to calculate this spring-based force. So first of all, we have two objects attached with the line. And obviously, what we can get is same as the other values, same as the other forces. We could get the mass for the object 1 and the mass of the object 2. Okay, and also we can get the lengths between the object. Now consider this is the initial length of the object, but we could also set a goal or target length, which can be said as like constraint length or target length. Let's call this target length as a TL. So TL, let's say TL could be smaller than the current length or bigger than the current length. And what's needed is to, in order to satisfy this target length, I kind of need to move each of the point to a specific direction. In this case, if the TL is smaller than the current length, then the object should go toward the center until it satisfies its constraint length. If the the target length is bigger than the current length, then the object should go further outward, separated each other until it satisfies the target length. In this, as you can see, for each line we need to calculate two vector values, one for object 1 and one for object 2. And based on the lengths, the target length and the current length value, it could be going inward or outward. So let's call this B1 and B2. B1 and B2. Okay, as a unit vector. And we also need to specify the force value, like how much it should go outward or inward. And that is the acceleration value. In this case, it could be a vector value. Now let's see how we can estimate or calculate this force value and as an equation. And maybe as an additional force, we could also have a gravity force if we are seeking for the three-dimensional space, real physical space. Then we also need to add this gravity force to each of the point. Meaning we have force 1 to be a spring, force 1 to be a spring force, and force 2 to be a gravity force. And the final force is, just call it F, is the addition of F1 and F2. Okay, we already done the gravity force, so I'm just going to look how we create this spring force. Okay, so let's call this F1 equal to, since this is a vector value, I'm going to use this unit vector V1 or V2. Let's start with the V1. So V1, okay, I shouldn't like this, V1 unit vector. And I also have to define the strengths of this force. Let's call this S, and S1, I guess. S1 is equal to, first of all, you can use the mass 1, and you could multiply it with a difference between the current length and the TL, the target length. If the current length is larger than the target length, then it should go inward, and let's make this positive value. If it's if the length is smaller than the target length, then this will be a negative. So in this case, let's go to the negative direction, which means it's outward. So let's say inward direction is the positive direction, outward direction is the negative direction. Now this force itself is not really a gravitational value, so we're not going to multiply like gravitation coefficient, but instead, if it's a spring force, you could have a stiffness, like how hard the spring is, okay? So we're gonna call this like ST as a stiffness. Or I'm just gonna call this S is already being used, so I don't know. N as a stiffness. Okay, so this is similar to a G, which is a coefficient value. Okay, now this could be the whole equation. So after all, the F1 is equal to B1 multiplied by mass 1 multiplied by the L minus TL multiplied by a stiffness, just like this. And probably might be a good idea to square this length difference to have a bit more natural like result or physical related result. We could check that out as well. For F2 it's pretty much the same. You just change the direction and change the mass, and the length difference is the same and the stiffness is the same. And probably I should multiply the mass 1 and mass 2 at the same time for V1 and V2, so probably I should multiply mass 2 here and mass 1 here as well, so that both of the at both points you have the same moving scale, the moving strength or force strength. We could try to see the difference later. So that's pretty much for it. That's pretty much it for a spring force. Let's try to implement it in Houdini with the VEX. Okay, first thing first, we need to set up the scene. So let's do that. I'm going to start by adding a single point at 0, 0, 0. This is going to be the first spring example that I'm going to create. I'm going to let's say set one point be fixed at specific point, so only a other point will move based on the length. So previously I was explaining that both point could move, but the first example that I'm going to show, I'm only going to move one of the point by fixing the other points. So let's say I'm only going to create force 1, and for the force 2 I'm just going to leave it as it is. I mean, set the point position to the fixed point positions. So in that case, the mass wouldn't really matter in that case. For the mass 2, so I could ignore this mass 2 and just ignore these value here. So this center point, the point at the 0, 0, 0 will going to be, the point is going to be fixed. Now let's also create the other point. Which can be placed manually. I'm gonna move it with this handle. It's a bit too big. Let's make this 2 by 2. Okay, now I'm going to set the second point to be a group of ball, just like we did for the pendulum. So ball, let's name this ball as a point. Now let's all initialize this point with some default attribute. So point wrangle init. First thing I would like to get set is the mass. So let's say 1.0, or let's make this parameters. I'm gonna start with the 1. I'm also going to set the target lengths. Like what would be the best length between this point and the first point, the center point. I can set it as a primitive attribute or point attribute. In this case, since there's only one line, I'm just going to set this to a point. If there's multiple lines, then it might make more sense to put it on the primitive attribute. Let's try both way. I'm gonna later on do it on the primitive. So target length is equal to chf target. Let's make it small, like 0.5. Right. Now that I have those 2 points, I'm going to merge these together. And create a line between those 2 points using another add node with the polygon option by group. Now the new line has been created. Now I guess I want those second line to be underneath, like in y direction, because I'm also going to apply some gravitational value, the gravity value. So let's make the initial positions to be -2 for the y. That's good. Alright. Now, also going to create some balls to the second point. So just for visual representation. Now, thing is that the spring might not always be like connected with the ball, but sometimes it's just like straight line string. So in that case, you don't really need to worry about the mass for both point, okay? But you just need to care about the mass for the whole like string, whole line. But in this case, I do have a balls at the end point, so I'm going to use the mass anyway. So I'm going to create the copy2 point, create the sphere node, connect it to this one here. As a target, I'm just going to use the ball. And let's also set the p scale based on this mass value. So f p scale is equal to mass multiplied by 0.1 or something. F at mass. Okay, and merge this ball together with the line. Alright. Okay, now what I want to do now is to move this point using the spring force to move in between this point, moving on top of this line to move either inward or outward, so that at some point the length between the point and the target, the ball point, will be close to the target length. Okay. So let's do that. I am going to create a solver for this line here. Okay, reconnect the line. Let's go inside the solver. Now let's create a point wrangle and filter this only act on a ball, since we only want to move this second point. Let's make this spring force. Okay. Now let's estimate the forces. Let's calculate the force. Checking back the equations. So F1 is equal to unit vector 1, which is in the inward direction, multiplied by the mass, and the difference between the lengths and the target lengths. And if it's power, then if it's square of its difference, then we might have to know the difference between the target lengths and the current length is either negative or positive in other equations. Okay, and multiply by the stiffness, and if there's other balls, then you could multiply with the mass, second mass as well. Let's, in this case, we don't have any second mass, so it's going to be a bit more simpler. Okay, so first thing first, we need to know, in order to get the direction, we need to know, currently we are looking at this point, but we also need to know this point positions to get the directional value. So let's get that first point positions, which in this case, it's pretty simple. It's at the 0, 0, 0, or we could also get the pivot positions at point 0, 0. Okay. And the direction V can be retrieved by pivot positions minus at P. Okay. Now I'm also going to get the lengths, which is going to be the lengths or the distance between the pivot pass and at P. Now for the V value, V directional value, I would like to make it normalized as a unit vector. Okay. And I'm also would like to get the difference between the target lengths and the current lengths. So this is the L is the current lengths. Now let's also retrieve the target lengths as a TL, where I have set this as an attribute called target lengths at a ball point. So float TL is equal to F at target lengths. It's like this. Okay, now the difference between these two lengths, I'll call this diff L, is equal to L minus TL. I'm gonna go with this for now and see what happens. Okay, now what else? I also need to have a stiffness, so let's call variable n and name this stiffness. Okay, gonna stop by 0.1 for now, which will be the coefficient value. So depending on those units, I might need to like increase or decrease based on the size of this stuff. Okay, now I think I have enough information to create the force. Let's try to create a spring force. So vector F1, which is going to be used as a spring force, is first of all comes V and multiply by a mass of the object, which is F at mass, and multiply by the difference between the lengths, so diff L, and multiply by the stiffness. Okay, which is named as N. Okay. Now I could add this to a velocity, which I forgot to create an attribute previously. So going in back to the init, going to create a velocity as a vector value starting from 0, which determines the speed and the direction. Okay, now let's update the velocity using this force value and check update the point position using this updated velocity. Okay, now I don't have any gravity force yet, but let's see what it happens with these, just with these forces. Okay, if I play it, now you can see that it's going back and forth in the singular direction. I think it is actually working. Now there is no dumping, so it's not like slowing down at all. So you might have to create some dumping force, dumping value as well, so that at some point it will just stops at the lengths that I want. Okay, so let's try to do that. I am going to multiply some dumping after I have calculated all the velocity, so somewhere around here. Velocity multiplied by dumping. Let's make it high enough, like 99. See what happens. And if okay, I think I have just changed the stiffness. Not this one, but instead what I need to change is, okay, I forgot to promote this dumping parameter. Let's call this 99. See what happens. So hopefully it slowly stop its movement. And try to make the lengths between the first point and the second point close to the target length, which I've set it as 0.5. So let's see what is the length between these current lines here right now. I'm going to create the measure node in between here and check the lengths. Set it as a parameter. See what it looks like. So previously it was like 2.5, and slowly the length is going close to the 0.5. Slowly and slowly it's changing its length, which got closer to the 0.5. Now to make those calculations, or to make these like movement get much faster to the 0.5, I might still need to use the square of the move difference, which should make the movement faster, the optimization faster. I mean, this is not the optimization, but the simulation faster. So let's make this power of 2. Now in this case, you don't have any more you don't know whether this is positive or negative anymore, so I'm gonna keep this as it is and then go back here. First of all, I'm going to multiply this by at the same value here, which will create a square value, and then going to multiply this diff L, which could be either negative or positive, and then divide by the absolute value of the diff L, which will create a point positive 1 or negative 1 with these equations. Now since this force is just for the half of the point, might also make sense to multiply by 0.5. If we have 2 points, then we do the half size force coming from this point and half size force coming from this size. Doesn't really matter at this point because you can like tweak it by changing this n value, but if you want to make it more realistic, you could do something like these. Okay, but in terms of the result, doesn't really much change, I think. Let's go back. Let's go back outside and see what happens. Now actually it didn't really change the speed, I guess. So in terms of the result, you can just choose either way. Actually, looks a bit slower. But this is more accurate way to calculate the forces. So if you like this way, I think that's better. If you are looking for, looking to use VEX for real physical like behaviors, then the one that I have just shown you is a bit more accurate, I think. Okay, now let's also try to implement the gravity force added to this spring force and see what happens. So currently this is the F1. Now let's add another gravity force. Call this as F2. And this is pretty simple. You just need to, first of all, create a 0, -1, 0, which is the negative y directional value as a unit vector, and multiply by a gravity for gravity coefficient. Let's call this gravity, and multiply by the current mass of the object. So let's set the gravity to small enough so that it wouldn't affect the spring that much. So like 0.01, something like that. And what I'm going to do, I'm going to add this velocity with F2 as well. Okay, now, and after that I can multiply with this dumping and use this velocity to update the point position. And let's see what happens. If I play it, now slowly it changes position going downward. Try to stop, try to keep this ball going downward, and at some point it will stop straight. And because it has the gravity force, the lengths become a bit longer than 0.5, I think. Yeah, it's getting multiple values. It's like double size of 0.5 because it's pulling downward. So if you want to keep the lengths between the point and the balls to be close to the target length as much as possible, then you might want to increase the stiffness of the spring or decrease the gravity force. Now let's say you cannot really decrease the gravity force, then in that case you might want to increase this stiffness value right here. Currently it's equal to 0.1. If I set it to 1, then it's really fast. It's not really stopping, isn't it? So in that case I might also have to decrease this dumping value. And the length currently is close to 0.5, getting close to the 0.5. So in the combination between the stiffness and the dumping is pretty important for the spring. If I increase the stiffness to 2, then I've set the dumping to 0.6 or something. Might give you a bit more faster result. Maybe too fast. 8. Oops, now it exploded. Sometimes if the stiffness is too big, then the force becomes really big for these calculations. Then it will just explode. So the balance is a bit important here. Let's make the dumping to 0.7. Okay, still too fast. Let's make the stiffness to 0.1. Alright, getting better. So you need to kind of find a balance. What's the best balance between the stiffness, dumping, and the gravity in this kind of cases. If the force becomes too fast, then you could also limit like the maximum force size, just like you did for the angular force or the the attractor force. Okay, so in this case, you could limit the maximum force size. Let's say F1 is equal to the length, normalize F1 multiplied by the length of F1 and calculate with the minimum, and so that we have another parameter for the max force 1. Okay, and then you can set some limitation here, like let's say 1, and by having this one might be able to have more higher stiffness and higher dumping. Let's check like this, much better, and you have a less a much closer value to the stiffness, I mean the target length. I set this 3. Getting better, like this. Okay, so this is a spring-based force value, and you can test out with other kind of parameters, like changing the target length bigger than the current state. So currently the length is between this point, and this point is currently somewhere around 3, I think. Yeah, 2 to 3. So let's increase the target length to 5 and see what happens now. In this case, it will try to expand its length to outward. Like this. And slowly going into the center because of the gravity. Alright, I think it's working. Let's also try with the other mass value. So I'm gonna set the target length to be 1 and the mass to be 2. See what happens. Now the the strength becomes faster because you have more mass, a higher mass object. If you make this 0.1 like this small, the movement becomes slower, and it because the dumping ratio is the same, it quickly reached to the equilibrium. All right, so that's for the spring force. And since we have done a single spring force, let's also try to implement what I have shown here using two forces, like one for one point and for the other point. And to make it a bit more interesting, let's try to create a chained spring force. Let's like creating a rope-like string, rope-like physics simulations using this same idea, same spring idea. Okay. I'm gonna group this one. I'm going to copy all this network. See how I can do it. Actually, the setup will be totally different, so I'm just going to delete this one and recreate the setup. So the one that I'm going to create is the chained string, which is going to be acted like a rope. Okay. So to do that, we need to create a bunch of lines connected to each other, like a rope. So first of all, I'm going to create a single line in extraction, probably, with the length of 5, starting with 5, like this. Okay, so let's create a bunch of points by raising up this point parameter. Let's set this to 20. Let's check. So I have a bunch of points, and in order to create a spring for each segments, I would like to convert it into a line connecting to each other. So to do that, I'm going to convert this polyline into a line using convert line node. Previously, it was just a single primitive, but now using by this one, convert line, I can have now, currently I have 19 lines. Okay, separated by the segment. It's good. And what I'm going to do is to simply do the exact same like line spring calculation for each of the line for both point. Each of the line, I'm going to calculate the spring force for this point and this point, for this line, for this point and this point, and so on, based on its lengths and the target lengths. So what we need for each lines, we need to get the current line lengths. So let's do that. Calculate the measure using the parameter. And let's also, since we're going to also apply some gravity, we have to pin some of the point so that it doesn't go like infinitely downward. So in this case, I'm just going to pin the first point and the last point. Okay, so that I could be able to create some kind of an arc-like curve using the gravity together with the spring force. Okay, that's what I would like to see here. So let's do that. I'm going to create a point wrangle. And then let's set the name to init. Okay, first of all, if ptnum is equal to 0, which is the first point, or ptnum is at the last point, which is equivalent to n points, the maximum number of points minus 1, then I want to set the point to be a pinned one, which shouldn't move. So let's create a group called pin. Okay. Now at each point I could set the mass, but I would like to consider that this whole string is like a single, like having the same thickness. So I am not going to consider the mass here. Okay, or I can just set the whole point to have the same mass. So let's say f at mass is equal to chf mass. So all the points share the same mass. Which doesn't really necessary, I think. And let's say 1.0. Okay. So as initial setup, I think this is fine, but for the primitive, I would like to set the target length for each of the lines. Okay. And to do that, I'm going to use the primitive wrangle this time. Previously, I have set the target length for the point, but in this case, I'm going to set the target length using the primitive wrangle to set as a primitive attribute. Okay. So I'm gonna name the attribute as target length equal to chf target. Okay, so currently the length for each line is 0.26. Actually, I could just pass this value as a target length, which might be okay. Yeah, which might be okay. So initially the target length and the current length is the same. So it's trying to keep its own like condition. So going back here, instead of creating the parameter, I'm going to delete this one. I'm just going to pass this current parameter. So parameter. Let's check this out. Going into the parameter. And the target length is the same as the parameter. Okay, that's good. Now, now that I have set up the object, let's create a solver. And one thing I would like to try is to currently both endpoint are being fixed, but it might be interesting if I could move one of the point interactively by using some cursor or handle. So let's try to do that. I am going to add a custom points which could be at the same point as the endpoint, somewhere around here, which maybe at the 0 is fine. So I'm gonna create a point at the 0, 0, 0 point positions, which is at the starting point of this line. And by changing this point position, I want this endpoint of the string to be stuck into this moved point, customly moved point by this handle. So if I move this handle, this point will always be fixed to this here, then the final result of the object will change depending on its disposition. Now that might be interesting, so let's try to do that. I'm gonna set this to 0, 0 for now. Okay, so let's try to implement this spring, just chained based spring. Okay, which is not that hard to do because we have already done for the single spring, and it's pretty easy to implement the similar stuff for every single lines, the multiple lines by just using a multi-threaded VEX. Okay, so in this case, I am going to use a primitive wrangle to access each of the line simultaneously. Okay. Okay, connect it to here, and I'm gonna name this spring force. Okay, and basically what I would do is to access for first of all, inside this primitive wrangle, I can access to each of the line. Okay, and from each of the line, I could get 2 points, the first point and the second point. And then using those points, I can estimate the direction, the V1 and V2, and also the mass and the lengths and so on. So let's try to get all those information first. First of all, I would like to get the number of points, the point numbers from this primitive using prim points, primnum. Now I know that there's only 2 points because every primitive is aligned with the 2 points. So I'm going to loop through all the points, which in this case there's only 2 loops, 2 iterations. And I'm going to create a PT1 and PT2. And PT2 is going to be the I plus 1, but if I is equal to 1, then I want this I plus 1 to be equal to 0. So I'm going to calculate the remains by the length of PTS. So in this case, if the I becomes 0, then I plus 1 is equal to 1. Yes, and if I is equal to 1, then I plus 1 calculated the remain by the length of PTS is equal to 0. That way, in the first loop, I can calculate for this point. If I'm looking at this line here, then the first loop I'm calculating the force for this point, and the second loop I'm calculating the force for this point using these setup. Okay, and let's also try to get the point position for each PT1 and PT2. In the first loop, the PT1 is this one, PT2 is this one. That's the first loop. In the second loop, the PT1 is this one, and PT2 is this one. Okay, so just by reversing the position or the point values, you can calculate the forces for each point at the same time. I mean, inside the loop by just using the same equations. Okay, it's pretty handy. Now let's get the point position at PT1 and point position at PT2. Okay, and also calculate the mass. We'll get the mass value from the point. It should be the same. Float mass 2.0. Alright. I might not really need these value here. And then calculate the directional value. Let's call this V, which is a normalized between the position 2 minus position 1. We also want the lengths between the position 1 and position 2, so let's calculate that. L is equal to the distance between the position 1 and position 2. Okay, and we also want to have the difference between the current lengths right here and the target lengths. So float a target length was f at target length. So the difference is float dl is the diff l is equal to a l minus tl. Okay. And now I can calculate the force value. Vector force is equal to B multiplied by, okay, just like we did last time. Since I have two masses, I'm just going to multiply those two altogether. So mass 1 multiplied by mass 2 multiplied by a different L. I'm going to create a square value for this differences, and then also create a negative or positive value by dividing the FL by the absolute value of the FL. So you can get either +1 or -1 as a value. Okay, just like we did for the single like spring. And last of all, I could multiply it with some stiffness. Let's also have this stiffness float n is equal to CHF stiffness. Okay, and let's set the stiffness equal to 1 for now. And as we did for the single spring force, we might also want to limit the force strengths. So force is equal to a normalized force multiplied by a length of force, and use the min function to limit the size with max force. Okay, and let's set this to something point. I'll start with 1. I'm not sure what's the best value here yet. Okay, so now after I have this force value, I can update the velocity for each point. I haven't created the velocity attribute, so let's do that inside init 7 here. I'm going to create a velocity attribute as a vector, starting with 0, 0, 0. Okay, going back inside the solver. Now I can update the velocity, and since if we check carefully, if we update the point position, 2-point position, which is attached to this line, so this point and this point, and updating the velocity, and if you go to the next line here, you are accessing to the same point right here, as you can see here. So you cannot override the velocity, but you have to add to the you have to increment, you have to add the velocity as an additional value to the previous calculations. And there's just an option for that in Houdini for VEX, so let's try to do that. From primitive wrangle, in order to apply the point attribute, you need to use set point attrib, and we are accessing to the velocity attribute. And at each loop, I'm just going to update the PT1 here, which is the first point. And the second loop, this point is going to be used for this line. So PT1, and I'm going to use the force to update the velocity with an option query called add, which will increment this force value into a velocity attribute. Alright, so I think this is fine in terms of adding all the velocity into a point. Now I think it's not a good idea to update the point position in this primitive wrangle, because it's simultaneously updating and using this add option for each point. So I want to make sure that all the point has been updated with the current velocity value. So after calculating all this velocity, I'm going to create another point wrangle, and that's when I want to update the point position. And probably I also want to add the gravity force with the point wrangle as well, because I don't need to do per lengths, per lines, but I need to do it per points for the gravity. So let's name this gravity force. Okay. To do that, it's pretty simple. You just need to create a, just like we did last time, gravity is equal to, or I'm gonna name this force is equal to set my 0 minus 1 0 multiplied by some gravitational force, so gravity, and let's call this 0.01 for the gravity. Okay, now I'm going to update the velocity with by multiplying the force, or maybe multiply adding the force and multiply by a mass of the current point position. And I think that's pretty much it for this one. Okay, so that's that. Now the gravity has been added on top of the spring force, and the velocity has been updated. Now last thing we need to do is to use this velocity to update the point position. Okay, so let's do that. Point wrangle, another point wrangle, update, pause. And we only want to look for where the point is not pinned. So if in point group 0 pin pt_num is equal to 0, if it's not pinned, then that's the point where I want to move. And in order to update the point position, it's pretty easy. You just need to first of all access the velocity. So vector val is equal to v at val, or I can just say v at val. And since we haven't set the dumping function yet, so let's also multiply the dumping parameter. Let's start by a big number like 0.95. Then update the point position by adding this velocity to the current point position. Alright, and let's try with these first. If I play it, okay, I'm having a little bit of problem here. It's going really downward. So it seems like the spring force is not acting properly. And let's see why. And probably that is because I'm forgetting to promote some parameters like stiffness. Or I do have it. So probably some parameter has not been set properly. So let me check. Okay, I have something wrong here. Has to be mass. So if I play it, okay, now looks like what I wanted to have. So currently I have the spring force to try to keep these the line lengths as much as possible to the original one, and also having the gravity force. Now currently I have it, the line is deforming a lot with the gravity. That is because the stiffness is not that high. So we might need to increase the stiffness a bit more if we want to keep this low, if this deformation to be low as possible. So let's try to increase the stiffness to 3 and see what happens. Oop, now it's going dancing. Seems like the stiffness is a bit too high. So we can make this max force to be a bit smaller. We still don't see a much of well, it's going up a little bit. We might also want to reduce the dumping a little bit, like 0.8. Getting a bit better result, I think. Let's make the stiffness to 10. Okay, a bit lower, getting lower. But I see that the point is kind of a jiggling. Might be a bit dangerous here. So I could... What if I do make it like 100? Okay. Now it's dancing again. Right, so instead of making this stiffness too high, I'm gonna keep it as 5. I could try to reduce the mass of each point, which is this one value. Let's make it 0.1 to see how does it affect. Now it goes slower. Still seeing a bit of deformations here. It's getting... I think I'm seeing a bit weird result here. It shouldn't go that far with this smaller mass value here. Let's see why. Okay, Okay, I see why. The reason is because I'm using the same mass for the gravity and the spring. And for the spring, I'd actually have to consider the thickness instead of the mass at each point. So I'm going to ignore the mass for the spring for now and just consider it as for a gravity. So going to the force for the spring force, I'm going to delete this mass multiplication and see what it does. Okay, now I think I see more lower result. And let's try to make it a bit more faster by setting the dumping a bit more larger value. So 9.5. Okay. Yeah, it's getting better, I think. It's getting stiffer and stiffer in this way. And if I try to increase the little bit of spring stiffness a little bit more, getting a little bit better, yeah. Just like this. Okay, and the last thing I would like to try is to try to create an interactive point position for one of the pin. So if I move this handle, then I want this line to follow this point that I have just moved. Okay, so how do we do that? It's not that hard to do. You just I have just connected this interactive points to the second input of solver, which can be accessed from this one. And at the last update, I can actually update the pin position by using this referencing point. So going here, and there is a, so this condition is checking if the pin is not at, if the point is not pinned. Now, else I can check if the point is pinned and if the point number is at 0. So else if the PT num is equal to 0, then I could move its point position to the reference point position from the second input. Just that. Now let's see what happens. Okay, I am going to play it. And if I move this point right here, okay, I'm seeing the duplicated cache. Okay, I might need to reduce the stiffness a little bit. It's getting a bit too dancey. So let's make this 2. Okay. And the gravity, I'm gonna make the gravity to, let's say, what was it previously? 0.01. I think that's fine. And I'm gonna set the mass to 1, back to 1 again. Okay, let's see. And I'm still seeing some cache here. It's not deleted. Let me reopen it. Okay, what's happening here? Ah, okay. I need to reset this position to 0, 0 as well. So 0, 0. Okay. Let's play this. And let's try to move this point position. And you can see that it's interactively changing its point, and the spring force is following its condition, just like I want. Now, I see a bit of problem here. The length between this point and this point and this point and this point is getting longer and longer. Yeah, that's obviously wrong. So let's try to fix that as well. And I think the reason is because I have limited the max force to be too small. So I have set it back to some bigger value inside the solver. For the spring force, I'm gonna set the max force to 1 and stiffness to 1 as well. Okay. Now let's see. If I play it, and try to move this point. Okay, I'm still dancing. Okay, not that good. Is it? I'm also going to make dumping a little bit smaller, like 0.85. And see what happens. Starting from 0, 0, 0. I move it. Yeah, getting better. Now I'm not sure why I'm seeing this cache each time. Looks weird. but I can see that it's working just fine right now. So by moving this point, I can see that the estimated a chained spring value is at the correct positions. That's good. That is good. Yup. So that's pretty much it for today. So what I have told you about is these set of forces, set of extended forces, which I haven't talked about, forces basic sessions. And the one that I have shown you today, how you could create your extended force, could be really useful when you want to create your own simulation or your own customized simulations. It even is helpful when you are using the dynamics, like DOPs from Houdini shells. And by understanding the basic like physics, how these basic physics substances working digitally inside a software, you could go deeper in with the DOPs as well. Especially for the vellums and pop grains, by understanding these basics, I learned a lot. Now, hopefully you'll find this interesting enough for you to experiment by yourself with these forces, maybe creating some custom forces by yourself. And the implementation that I have told you today as a physics-based simulation is just a simplified version of the physics simulations. If you check like source code or other like simulations, it's more sophisticated. It has more forces. It has more equations to make the simulation stable. As you can see, what I have implemented sometimes have some bugs when spring starts to dance and so on. So if you want to make it stable, you have to have more like calculation done in order to, but the basic idea is the same. So once you know the idea, you'll be able to like extend it for your more complex kind of forces. And it also helps you understand how the existing force physics library works. Okay, for the next topic, I would like to talk about the basics of recursive, like a fractal shape and so on, using such as for each loop or solver. Okay, that's it for today. Thank you very much for watching. And if you liked the video, please like and subscribe. And I'm also doing the Patreon myself, so if you are kind enough to support me, I'll be appreciated that you can access to my page from the video description page of this video. And every Wednesday I'm doing the Algorithmic live tutorial around at 10 p.m. on 10 p.m. Japan time on Wednesday. So if you're interested, I would love to have you as well. Okay, thank you very much and see you next time. Bye.